Well, thank you, Jairo. But most importantly, thank you, Garrett, for putting this great program together. My job is relatively easy. All the background information that I need to present my stuff has been discussed already. So I'll refer to some of those things throughout my talk. I left the topic quite general, and you've seen already many aspects of spin transport in insulators, and I guess I don't have to motivate why this is interesting. Low dissipation, on the one hand, is some kind of overarching motivation, but also sort of a desire to look for some novel collective nonlinear effects. And in this talk, I will emphasize some rudimentary aspects of topology, which start playing out regarding spin transport in insulating systems. However, in this talk, because of the emphasis of this program, I will try to sort of shift as much focus as I can within my research onto the microwave dynamics, so the microwave dynamics aspects of spin transport in insulators, however, still coupled and driven by thermal or electrical or some kind of thermoelectric tools. Also, there are connections to some natural connections to quantum impurities, which could naturally couple to collective dynamics, like has been mentioned by Amir already. The work has been done over the last few years in collaboration with various postdocs in my group and senior colleagues in Europe, States, experimentalists and theorists. So I'm going to be reporting on behalf of these people. All right. So also in the spirit of this meeting, I want to study transport and magnetic insulators in various regimes of signal transducing. Okay, so I will I will basically look at conversions between different signals. On the one hand, I have so these are all very well-established signals that could be applied to magnetic insulators. Thermal through the Spin-Zebek effect, as was nicely presented by Saito sensei. Electrical through the spin-Hall effect primarily, as was also discussed in the previous tutorials. I can also couple to quantum impurities very naturally via collective microwave excitations and magnetic insulators. And that has been discussed by Amir. So these are sort of extraneous signals or systems that I can now quite effectively couple to magnetic insulators on the one hand, and on the other hand, of course, I have natural excitations in the simplest scenarios that I can decompose into some kind of magnon transport, magnon dynamics. Okay, so you could think of using magnetic insulators to bridge these various phenomena with different reincarnations of magnonics. Classical in this talk for the most part, but also with definitely clear outlooks towards quantum effects. Okay, and I want to think also to appeal to this community about magnetic insulators as sort of islands as coherent microwave cavities. Okay, so I'm not going to have additional microwave cavities. So collective excitations in my magnetic insulators will play the role of the cavity. Okay, as a result, I will be relying primarily on the exchange interactions, very strong interactions. Okay, so most of the effects I will discuss will be rooted in the exchange interactions. So I will naturally be in a very strong coupling regimes. All right, so the outline for my talk, quite ambitious, but not as ambitious as some of the previous talks. So there are a few topics. So I will start with an introduction of magnetic insulators as a transport medium, specifically emphasizing the two-fluid way. So many people talked about the coherent aspects of magnetic dynamics. Many people, especially in the recent talks, talked about incoherent aspects carried by thermal magnons. In this talk, I want to discuss those two on equal footing, and I actually want to make the coherent and incoherent aspects talk to each other. So you could think of that as a two-fluid perspective. One fluid is normal, the other fluid is coherent. And certain regimes that might be reminiscent of two-fluid theory of superfluidity, specifically in easy plane spin dynamics, using the language of spin condensate to describe the coherent easy plane precession of spin. This two-fluid language is very natural, and the coupling between the thermal component and the coherent component is also quite strong and very natural, and in many respects analogous to similar phenomena in superfluids, superconductors, or neutral superfluids. Okay, so like I said, I want to emphasize the microwave aspects of this dynamics in this talk. Again, with the focus on easy plane materials, easy planes of naturally easy plane or somehow effectively easy plane, like the systems that Burkert was talking about. When you a generic system pump heavily, it sort of effectively becomes easy plane because there is a dynamic order parameter that breaks U1 symmetry. That's the starting point for discussing condensation and possibly even superfluidity. I'm happy that triplet superconductivity was already mentioned earlier today, so then this should not appear too exotic towards the end of my talk. And maybe the last topic that has not been mentioned, I will just, I'm quite excited about it, I just want to flash it, just to advertise at the end of my talk. And it's this phenomena, but based on disordered glassy magnetic systems. Okay, so we've heard a lot about magnons as a building block of how you think of excitations in ordered magnetic materials. Okay, of course, the starting point is one can think of it as coherent magnons, some kind of FMR type of signatures, both in ferro or antiferromagnets. So magnetically with net magnetization or without net magnetization. And recently, of course, the coherent aspects have been studied for a long time, but recently the incoherent cloud of these magnons has also gained some prominence in various transport phenomena in the context of spin-Hall, spin-Seebeck type of drives. In my talk, I want to emphasize the other kinds of collective excitations which are distinct and but just as abundant in magnetic materials, just as generic. And these are topological textures, such as winding textures in easy plane materials, or some skyrmionic textures in more isotropic materials, or could still be anisotropic, but sort of like three-dimensional magnetic orientation, having some topological aspects. Okay, so in general, in any kind of ordered material, it's not that one should invoke only the Gaussian modes. On equal footing, to understand both equilibrium properties, and I want to make a case here that also non-equilibrium transport properties, one has to on equal footing understand the topological defects and topological aspects of collective dynamics on the one hand, and on the other hand, the small angle fluctuations with respect to the topological textures, those are magnons, and look at the interplay between the two. So that is certainly the spirit of two-fluid theory of superfluidity. And I want to emphasize in this talk that many of those aspects extend to the magnetic systems and are actually much richer. In fact, turn out to be much richer. In easy plane, they are just like neutral superfluids, but in general, they could be much more diverse and rich and interesting to think about, and certainly promising utility also that we can try to anticipate. As has been already mentioned in Burkert's talk, diffusive type of transport, of course, in condensed matter is not the only possibility. Superfluidity is another prominent example of transport, and already there are some signatures of superfluidity in magnetic systems, as has been discussed. But essentially, it's the collective transport of this nature in which the current that enters some continuity equation is not given by the gradients of some inhomogeneous thermodynamic potential, like temperature chemical potential, but the gradient of, let's say, phase in the case of easy plane dynamics, or in general, some kind of expression that's written in terms of the coherent order parameter. Easy plane material, easy plane doesn't have to be ferromagnetic, it could be antiferromagnetic. Any material with an XY order parameter that breaks rotational symmetry around the z-axis is a very good starting point to think about such a collective superfluid-like effects. And a few years ago, we proposed sort of more like a conceptual type of setup in which you could manifest the superfluidity, spin superfluidity, through a long-ranged two-terminal spin transport mediated by an insulator. And we suggested to use one edge for spin injection using spin Hall effects. So electrical current would be sent in this direction. That induces spin current polarized out of plane. That's the symmetry axis. That's the axis around which we have hydrodynamic description for spin flow. The spin is injected. It induces some texture, order parameter dynamics. And then at the other end, via a combination of spin pumping and the inverse spin Hall effect, you have a detectable signal. And the key to this type of long-ranged signal, so the salient feature aspect that makes such signals distinct from signals mediated by normal quasi-particle flow is the long-rangedness. The quasi-particles decay, so there's some spin diffusion length. Any signal that you would try to transmit across the insulator via magnons or other quasi-particles would always have a finite propagation length, would always have a decay length beyond which the signal is exponentially suppressed. In practice, one might say, wow, the decay length is long enough. Maybe for applications, one should not care about it. But conceptually, this is very important. So those are all short-ranged currents. If instead you transmit signals via topological textures, like in this case, a winding texture associated with the order parameter, then because the winding cannot locally decay, or it's very difficult for it to decay locally, it would require overcoming some large energy barrier, so the decay processes could be exponentially suppressed. The signals end up to be algebraic, not the exponential. Okay, so they will decay eventually, but only algebraically. So if you combine this interfacial physics of injection detection together with some kind of LLG theory for this order parameter dynamics, you expect the non-local signal to go like this. Mu is the spin accumulation that you supply, and this is some effective impedance of this order parameter with the mixing conductances standing for the impedance of the interfaces. And then there is a parameter here that parameterizes dissipation in the system, Gilbert damping, and that scales with L, the length of this channel. So there is no exponential suppression. It's algebraic, long-ranged. And there are a couple reports already out, experimental reports that seem to, well, at least claim to exhibit this physics. There's one on chromium-203 that has been mentioned already, another one on a canted antiferromagnet state in graphene, subjected to very large, basically in the quantum Hall regime. So I think there's quite a bit of interest. People want to see. It would be great to observe these effects, but I would say that still these claims are quite tentative. Experimental claims are quite tentative at this point of time, and it remains to be convincingly detected yet. But theoretically or conceptually, there are many good candidates for such spin superfluid phenomena. So easy plane magnet is a good candidate, YIG perhaps. But on the antiferromagnetic side of things, there are even more candidates. Basically, almost any antiferromagnet would be a good starting point. if there is a natural easy plane in an antiferromagnet, that's all you need. If you have more generically an easy access antiferromagnet, such as manganese fluoride, chromium oxide, so if a generic antiferromagnet with a preferred orientation, you could kill, that's kind of the beauty actually of antiferromagnets in this context. You can kill that easy axis by applying large enough magnetic field along that easy axis. So applying magnetic field for ferromagnet, antiferromagnets, unlike for the ferromagnets, it creates the easy plane perpendicular to the magnetic field. The Néel order wants to be perpendicular to the magnetic field, as Sebastian already discussed. So overcoming easy axis anisotropy, if it's not too strong, is possible with the magnetic field. That's called spin-flop transition. And then beyond the spin-flop transition, the remaining high symmetry dynamics within the easy plane is the starting point for XY model and the associated spin superfluidity. There's a class of materials that have been discussed years ago as triplet condensates, and the phenomenology of them is the same. They effectively XY antiferromagnets. So also good materials to look for spin superfluidity. And all that is required experimentally is well, to have well, good films of these materials, put platinum contacts, and see if spin Hall, spin Zebek type of physics, also SMR for starters, if those kind of if that physics works out, and then one can try to, as a next step, try to look for non-local signals transmitted by these materials as a signature of collective topological hydrodynamics. So those are kind of natural condensates. There are also pumped condensates, as has been discussed by Burkhardt. I don't want to repeat any of his presentation, but I just want to say that if you, so another generic route is to start with a pretty generic magnetic system, and under the appropriate pumping condition, you can achieve basically overpopulating bosons can achieve reach a condensation instability, and then that condensate has a dynamic order parameter, whose basically phenomenology, at least as far as non-equilibrium properties are concerned, is very similar to the equilibrium XY model. So that's also a good starting point for spin superfluidity. And some of the, again, there are some tentative claims, as has been put forward by Burkhardt, that there seems to be some signatures of spin superfluidity also in this pumped system. So I think there are already indications here and there that maybe this will develop, and we'll see hopefully more sort of collective spin superfluid-like aspects in transport of magnetic insulators, rather than just simple spin wave transport, spin wave mediated transport. So one more thing I wanted to mention somehow to really present a complete story is that, of course, parametric pumping is not the only way to create non-equilibrium condensates. One can also create non-equilibrium condensates by thermodynamic pumping. So one way to do it that's easy to understand is essentially to drive a spin-Zebek effect, the spin-Zebek effect that AG presented, to drive it into the nonlinear regime. If you apply, let's say, put a platinum on top of something like Higg and drive a large thermal gradient, the platinum injects a spin current. That creates excess of spin accumulation with non-equilibrium magnons in Higg, and at some critical threshold, they can condense. Formally, this is very much like the rapid cooling. In fact, it's the same thing conceptually as the rapid cooling that was also mentioned by Burkhardt, in which you start with a hotter Higg in equilibrium and then rapidly cool it down. So then you have an excess magnons at an ambient temperature. So basically the goal is to create an excess magnon at whatever ambient temperature, and at some threshold they will condense. So bosons always condense. You just have to have a mechanism to get many of them. What's that?
They don't need transport with rapid cooling.
Well, no. No, you need, it's the same thing, just different regime of the same physics. You need transport because, first you heat it up, so the magnets come from somewhere, and then you turn off your heating, so they just kind of, they're there and oversaturated. You don't need transport in a sense, like, you just waited for a long time for those magnets to come in, so the transport happened, you just don't care about it, but then the downside is a pulsed experiment. So a condensate is a transient phenomenon, while here, it's like, it's a DC condensate. You turn the switch on, and the condensate is there. It's like you created a new non-equilibrium material. You turned on your switch, and you switched, from an ordinary ferromagnet to basically a superconductor, which is there permanently, not in some kind of transient state. All right, and that has been observed recently in the group of my colleague in California, Irvine, Ilya Krivorotov, by basically realizing the structure that I've shown already, putting platinum on top of here, cranking up electrical current through platinum. And the electrical current, it does essentially nothing, the way we understand in this experiment, but heating platinum, just due to Joule heating, that and via spin-Seebeck effect that injects magnons into YIG, and then at some point these magnons condense at some critical threshold of the DC current. And the beauty of the setup is that there's a little bit of SMR, spin Hall magnetoresistance, at the interface. So when the magnons in YIG condense, YIG starts processing coherently, and it's a pretty large strip. It's like 15 microns long, and processes coherently over the distance of 15 microns. And we know that it processes coherently because it emits, through this contact, it emits, this dynamics emits microwave radiation that is quite, well, first of all, just any radiation that comes out would require coherent precession of YIG, and the line width is quite narrow. So unlike, I think that's kind of one of very, very few, if not almost the only demonstration of really coherent dynamics of YIG beyond some condensation threshold. So it's not that we see some kind of overpopulation at low energies. We really have evidence for the coherence, which is really key. Finally, the physics that Amir was talking about regarding, well, Amir was talking about a bunch of things, but one of the things he was talking about is using NV center to detect a noise emitted by ferromagnetic films. The ferromagnetic films could be driven by spin-Seebeck effect, by spin Hall, by microwaves that drive generally shifts the chemical potential of magnons excited on top of, let's say, some coherent dynamics in my magnetic film. And that chemical potential can be detected by the NV center, as Amir convinced all of us, hopefully. The physics of shift of the chemical potential of magnons by the coherent precession of YIG, of the ferromagnetic order parameter, is exactly reciprocal of the physics of the thermodynamic Bose-Einstein condensation. So it's just the same physics, but in the sense of Onzaga reciprocity going in the reverse. So in Bose-Einstein condensation, you create overpopulation of magnons, which precipitate growth of the condensate. Condensate is just the coherent dynamics. Here, you put in the condensate by hand, simply by FMI excitation, and that evaporates, shifts the chemical potential. And that shift of the chemical potential actually is very well visible by the NV center. So the relaxation rate of the NV center is very sensitive to the shift of the chemical potential, and that can be easily detected. So that's quite nice, and I want to emphasize that the NV center in principle here senses both the aspects of the coherent dynamics via the stray fields and the incoherent dynamics via the relaxation. So integrating quantum impurities with this to fluid dynamics to control both, let's say, some kind of splitting, some kind of, like in the language of quantum computing, some kind of single qubit aspects, as well as 2-qubit gates, and also controlling the dissipational aspects of the environment. That all seems kind of feasible. So yeah, I think interfacing quantum impurities with the fluid dynamics seems like a very interesting direction that we're also thinking about. Okay, finally, let me go back to these types of structures, and let me discuss some microwave aspects that I thought could be interesting to this community. So again, let's go back to this terminal setup with something like 2 platinum strips, which couple to magnetic dynamics via the spin-Hall, inverse spin-Hall effect, to the easy plane dynamics that I said maps onto, captures some spin superfluid aspects. If you drive electrical current, as shown in this left panel, sort of to go around this XY magnetic region, then that will trigger essentially uniform precession of the order parameter, because you have both spin up here and spin up here induced by spin-Hall effect that are impinging from all sides onto the ferromagnet, and in the steady state that puts the collective XY dynamics into some steady state precessional motion, which corresponds to this incoming spin current being balanced off by spin pumping outwards, as well as some Gilbert damping in the interior of this ferromagnet. If, however, the structure is like this, the electrical current, you make electrical contacts like this on the same, let's say, structure, so electrical current goes up and up on both sides. On the left, you inject spin current. On the right, you drain spin current. So then you, in the steady state, you create a static texture. There's no dynamics because you inject on net 0 spin current, but there is spin current flowing from left to right. So that triggers a gradient of that induces a gradient of phase, because that is necessary to carry spin current collectively. So then you have in the steady state the static and inhomogeneous configuration, or if we drive, let's say, apply some current, and in a second that current will become microwave on one side and detect the voltage on the other side. Then you have both dynamics and texture. That's all nice. However, the problem that one can immediately recognize is that the moment you introduce some anisotropies within the XY plane, at least in the linear response, the dynamics will be quenched because the magnetization will simply be pinned by the anisotropy, and then you have to overcome that anisotropy, so you have to go to the nonlinear regime. Alternatively, and that connects us to some microwave features that we studied a couple years ago in this paper. Alternatively, you can, instead of thinking about DC transport, you can apply AC voltage to the, let's say, input contact, and that allows the signal to be transmitted from left to right. And that transmission, so in the absence of anisotropy, the transmission, so the microwave, non-local microwave resistance, so AC trans resistance in this structure, would have a bunch of peaks. There would be a peak at 0 frequency, so that corresponds to the fundamental Goldstone mode, to the superfluid. And then there will be higher peaks corresponding to the standing waves. Okay, so the spacing between these peaks is given by the superfluid velocity divided by the distance. So each peak corresponds to the standing wave. If you have anisotropy, the anisotropy quenches the 0 frequency peak. So nothing happens at 0 frequency. So the superfluidity is quenched at 0 frequency. But the moment you go to finite frequency, so the dashed line corresponds to this trans resistance in the presence of anisotropy, you basically see very, very similar structure, simply shifting the superfluid peak to a peak corresponding to the essentially Kittel mode type of frequency of the dynamics. And then the standing waves, which at high enough wave number become basically coincide with the standing waves of the superfluid. So at finite frequency, you don't really worry so much about the anisotropies, and then the superfluid analogy becomes even more useful, because anisotropy is not so detrimental as it is for the DC transport. Now, in the remainder, well, I guess I ran out of time, but just give me a minute or two just to flash a couple recent results that built on the same physics, but in very different systems. So in a recent paper, together with our colleague in Korea, Sukbum Chan, we proposed the same kind of ideas to study spin superfluidity in this famous material that is probably the best candidate out there for triplet superconductivity, strontium ruthenate. And it's a great material because there's another material, very similar, another strontium ruthenate with a different, slightly different chemistry, but very compatible lattice-matched crystal structure, which is ferromagnetic. So you could use this 113 strontium ruthenate as a ferromagnetic spin injector, and then the superconducting. So this is a triplet paired p-wave superconductor as a medium for spin superfluid transport. Okay, so here the ordinary charge superfluidity exists with spin superfluidity, and in this two-terminal measurement, we can sort of decouple two if we switch. So if we look at the transport with different magnetic orientations, different in absolute sense and different in relative sense. Okay, so without going into much more sort of details, I just wanted to emphasize that the spin flow here formally, you could think of it as a flow of up and down Cooper pairs from left to right, sort of using the conventional, more like conventional picture, familiar to people, more like traditional people in this context, like Tony Laggett. So it's a beautiful review on this kind of materials. But the same, just different representation, but essentially the same. You could look at this physics can be represented also as the easy plane order parameter dynamics. In this case, that order parameter is what's known as the D order parameter is basically the spin component of the superconducting order parameter. So the up, down Cooper pair flow corresponds precisely to texturing this D order parameter within the easy plane. So formally, and then the Leggett something is known as the Leggett equations for the triplet order parameter dynamics actually maps onto our story of the XY magnetic dynamics, and we can sort of study the non-local transport in exactly the same fashion as before. I just want to just mention that the injection and detection here of spin happens not via the spin Hall effect, but via spin polarized Andreev reflection at the interfaces. But you could also use spin Hall effect if you want in a different geometry. That's nice. And one more thing that we kind of get for free, that's something that that community has not realized before, is that there's also Gilbert damping. So the triplet order parameter dynamics suffers Gilbert damping, and that might be sort of the dominant dissipation mechanism in these materials, because there's no dissipation in the charge spectrum. All right, and like I said, I just want to flesh our proposal to realize something that we call an SU2 superfluid in spin glasses, in which you utilize you randomize magnetic anisotropy. So this could be amorphous YIG or any, in fact, generic amorphous or disordered ferro or antiferromagnet. All we need is a strong short-range order, sort of glassy short-range order of magnetization on some kind of atomic or mesoscopic scales, but no long-range order of any sort on macroscopic scales. And then we propose that this material can act as a very robust, ideally in certain cases, very robust isotropic superfluid. Isotropic in the sense that you could transmit spin, no matter how you inject it. Let's say you put a platinum contact on top, on the side, no matter what the spin quantization axis for injection, that will propagate through this glassy material as a superflow. And the superflow corresponds to three-dimensional rotation of this microscopic texture around the spin quantization axis of your injected current, which is determined by the geometry of the spin Hall effect. So the detection then has to be compatible. You know, if you put platinum contacts on top for injection, then the detection should also be on top. If you put the injector on the side, then detection should also be on the side. Remarkably, this glassy material can carry spin polarized in any direction. Okay, so there is no requirement for any kind of easy plane anisotropy. It's just the nature of the order parameter, which is now like a three-dimensional rigid object rather than a sort of a directional order parameter. Okay, let me skip that. I wanted to make some take-home messages. Please read them, and thank you, and thank the funding agencies.